The circle is one of the most fundamental shapes in mathematics and in our world. Today, we're going to explore its key properties and discover the formula for its circumference. Here we have a perfect circle with a radius of 2 units. You might notice that every point on this circle appears to be the same distance from the middle, which is exactly what defines a circle. This yellow dot represents the center of our circle. What makes a circle special is that every single point along its edge is exactly the same distance from this center point. This equal distance property is what gives circles their perfect roundness. This red line shows the radius of our circle. The radius, labeled as r, is the distance from the center to any point on the edge. For our circle, the radius is 2 units. No matter which direction we measure from the center, this distance will always be the same. When we extend the radius to go all the way across the circle through the center, we get the diameter, shown here in blue. The diameter connects 2 points on the circle and always passes through the center. Since it's made up of 2 radii extending in opposite directions, the diameter d is always equal to 2 times r, or 2 times the radius. Now let's focus on the circumference, which is highlighted in green. The circumference, labeled as c, is the total distance around the circle. If you were to take a string and wrap it exactly once around this circle, the length of that string would be the circumference. The question is, how does this circumference relate to the radius we saw earlier? Throughout history, mathematicians noticed something remarkable when comparing the circumference of a circle to its diameter. For any circle, no matter its size, when you divide the circumference by the diameter, you always get the same number. This special number is approximately 3.14159, and we call it pi. This discovery gives us the formula for the circumference of any circle, c equals 2 pi r. Since the diameter equals 2r, we can also write this as c equals pi times d. This means that for our circle with radius 2, the circumference would be 2 pi times 2, which equals 4 pi units, or approximately 12.57 units. The beauty of this formula is its simplicity and universality. No matter how large or small a circle is, its circumference will always be exactly 2 pi times its radius. This relationship between the radius and circumference is one of the fundamental properties that makes circles so important in mathematics and in our world. Let's explore how a circle's circumference can be understood through regular polygons. We'll start by looking at a circle with a radius of 2 units. If we inscribe a triangle inside this circle, connecting 3 equidistant points on the circumference, we get a regular polygon. This triangle gives us a first approximation of the circle's shape. To find the perimeter of this triangle, we can use a general formula for any regular polygon inscribed in a circle. The formula is the number of sides times 2 times the radius times the sine of pi divided by the number of sides. This accounts for the length of each side of the polygon. Let's plug in our values. For our triangle, we have 3 sides and a radius of 2 units. So our perimeter calculation becomes 3 times 2 times 2 times the sine of pi divided by 3. What happens if we increase the number of sides? Let's look at a name with n sides inscribed in our circle. As we add more sides, our polygon will better approximate the circle's shape. We'll use the same perimeter formula, but now with n sides. Notice how each side of the name is closer to the circle's curve than our previous polygon. As we increase from n-3 if n3 else 3 sides to n sides, the perimeter increases from perimeter value 0.5, 2f, to perimeter value 2f. This is happening because our polygon is getting closer to matching the circle's actual circumference. Each additional side allows the polygon to hug the circle more tightly. Now, let's dramatically increase the number of sides and see what happens. We'll quickly move from 12 sides all the way up to 96 sides. Watch how the polygon becomes almost indistinguishable from the circle as we add more sides. This demonstrates a fundamental idea in mathematics. A circle can be thought of as a regular polygon with an infinite number of sides. As our sides approach infinity, the polygon's perimeter approaches the circle's circumference. Looking at our 96-sided polygon, its perimeter is approximately 12.57 units. This is remarkably close to 2 pi times r, which is 2 pi times 2, or 4 pi, which equals about 12.57. This is not a coincidence. As the number of sides approaches infinity, the perimeter formula converges to the circle's circumference formula, 2 pi r. This convergence reveals the famous formula for a circle's circumference, c equals 2 pi r. In our example with radius 2, the circumference is 2 pi times 2, or 4 pi, approximately 12.57 units. This relationship between polygons and circles helps us understand why pi, approximately 3.14, appears in the circumference formula. Let's explore an interesting property of circles by examining circles of different sizes. Circles appear everywhere in our world, from wheels to planets, and their properties follow consistent mathematical patterns. For each circle, we'll draw a line across to show its diameter. The diameter is the longest possible straight line that passes through the center of a circle, connecting 2 points on the circle's edge. Now, let's unwrap the circumference of each circle into a straight line. The circumference is the complete distance around the outside of a circle. Imagine taking a piece of string, wrapping it perfectly around a circle, then straightening it out to measure its length. Watch as we unwrap our smallest circle first. Notice how its curved circumference becomes a straight line. Now the medium circle unwraps into a longer line. And finally, our largest circle unwraps into the longest line of all. Let's label these lines as C sub 1, C sub 2, and C sub 3 to represent the circumference of each circle. Now let's calculate the ratio of each circle's circumference to its diameter. This ratio tells us how many times longer the circumference is compared to the diameter. For our small circle, if we divide the circumference C sub 1 by diameter D sub 1, we get approximately 3.14159. For our medium circle, the ratio of C sub 2 to D sub 2 also gives us approximately 3.14159. And for our large circle, the ratio of C sub 3 to D sub 3 gives us the same value, approximately 3.14159. Notice something remarkable? No matter the size of the circle, the ratio of circumference to diameter is always approximately 3.14159. This is one of the most fascinating discoveries in mathematics. This number appears everywhere in nature and mathematics. Let's fade out everything except one circle to focus on this important relationship. This will help us derive a formula for finding the circumference of any circle. This constant ratio of circumference to diameter is so important that mathematicians gave it a special symbol, pi. Pi is an irrational number, which means its decimal representation never ends or repeats. We typically use 3.14 as an approximation, but its exact value cannot be written as a simple fraction. If we rearrange our ratio equation, we can write c divided by d equals pi, which means c equals pi times d. This gives us a simple formula for finding the circumference of any circle when we know its diameter. Since the diameter is twice the radius, we can also write this formula in terms of radius. If d equals 2r, then c equals pi times 2r, which simplifies to c equals 2 pi times r. This is the formula you'll use most often to find a circle's circumference. To recap, we've discovered that for any circle, the ratio of circumference to diameter equals pi, approximately 3.14159. This gives us two useful formulas, c equals pi times d, or c equals 2 pi times r. These formulas work for circles of any size, from tiny atoms to giant planets. Now that we understand what pi represents, let's derive the formula for calculating the circumference of any circle. We start with the definition of pi that we just learned. Pi equals c divided by d, where c is the circumference and d is the diameter of the circle. This ratio is the same for all circles, which is what makes pi such a special number. To find a direct formula for the circumference, we need to rearrange this equation. If pi equals c divided by d, then we can multiply both sides by d. On the left side, d and d cancel out, and on the right side, we get c equals pi times d. We know that the diameter of a circle is twice its radius, so we can substitute d equals 2 times r into our equation. This substitution is useful because in many geometric problems, we're often given the radius rather than the diameter. When we substitute d equals 2r into our equation c equals pi times d, we replace d with 2r. This gives us c equals pi times 2r, which we can rewrite as c equals 2 pi r. This simple transformation gives us the standard formula for the circumference of a circle in terms of its radius. So here's our final formula, c equals 2 pi r. This means the circumference of any circle equals 2 pi times its radius. If you know the radius of a circle, you can easily find its circumference by multiplying the radius by 2 pi. For example, if a circle has a radius of 5 centimeters, its circumference would be 2 times pi times 5, which equals 10 pi centimeters, or approximately 31.4 centimeters. This elegant formula works for circles of any size. Whether it's a tiny circle the size of a dime or one as large as a planet's orbit, the circumference is always exactly 2 pi times the radius. That's the beauty of mathematical relationships. They reveal consistent patterns across all scales. Let's explore the formula for the circumference of a circle, one of the most important measurements in geometry. The radius of a circle, shown here in red, is the distance from the center to any point on the circle's edge. This key measurement will help us understand the circumference. The circumference is the total distance around the circle, the complete perimeter that wraps around the shape. We're going to trace it in green. The formula for the circumference is c equals 2 pi times r, where r is the radius. But what does this formula actually mean? Where does this number pi come from? To understand this formula more intuitively, we can imagine cutting the circle at one point and unwrapping it into a straight line. The length of this line is exactly the same as the distance around the circle. This straight green line represents our unwrapped circumference. Its length equals 2 pi times the radius. But to really understand what this means, let's see how many radius lengths we can fit along this line. Let's mark out segments along our line, where each segment has exactly the same length as the radius. The first segment is labeled r to show it equals 1 radius length. Amazingly, we find that we can fit exactly 2 pi radius lengths along the circumference. This is why the formula is c equals 2 pi r. The circumference contains exactly 2 pi copies of the radius placed end to end. Let's explore this concept further by looking at a semicircle, half of a complete circle. Since a semicircle is exactly half of a circle, its arc length, or partial circumference, should be half of the full circle's circumference. If c equals 2 pi r for a full circle, then a semicircle's arc length equals pi r. When we unwrap the semicircle, just like we did with the full circle, we get a straight line. The length of this line is pi r, exactly half the length of the unwrapped full circle. Just as we did before, we can mark out radius length segments along our unwrapped semicircle. We find that exactly pi radius lengths fit along a semicircle's arc. This confirms our understanding that the semicircle has half the circumference of a full circle. Now let's return to our full circle and visualize how 2 pi radius lengths actually fit around its circumference. Imagine drawing radius lines from the center outward, like spokes on a wheel. Each of these red lines is exactly 1 radius length. If we were to take these radius lines and place them end to end along the circumference, we would need exactly 2 pi of them to go all the way around. This is why the circumference equals 2 pi times the radius. So our formula c equals 2 pi r isn't just a rule to memorize. It represents a real physical relationship between the radius and the distance around the circle. To summarize, the circumference of a circle equals 2 pi times its radius because exactly 2 pi radius lengths fit around the circle. This beautiful relationship works for circles of any size. As the radius gets bigger, the circumference grows proportionally. Now that we understand the formula for the circumference of a circle, let's see how it's used in everyday life. The formula c equals 2 pi times r connects the distance around a circle to its radius in a beautifully simple way. Let's start with a bicycle wheel. Typical bike wheels have a radius of about 13 inches. This measurement is from the center of the wheel to its outer edge. Next, consider a medium-sized pizza with a radius of 7 inches. Pizzerias often describe their pizzas by diameter, but we need the radius for our formula. Finally, let's think bigger, much bigger. Our planet Earth is nearly spherical, with an average radius of approximately 3,959 miles. That's the distance from Earth's center to its surface. To find the circumference in each case, we simply apply the formula c equals 2 pi times r. For the bicycle wheel, we multiply 2 pi by 13 inches, giving us approximately 81.7 inches. This is the distance the wheel covers in one complete rotation. For our pizza, the circumference is 2 pi times 7 inches, which equals about 44 inches. This measurement tells us how much crust is around the edge, useful information for both pizza makers and hungry customers. For Earth, the calculation is 2 pi times 3,959 miles, giving us approximately 24,874 miles. That's the distance you would travel if you could walk in a perfect circle around the equator. Amazingly, this same simple formula works at every scale, from tiny circles to planetary ones. The relationship between a circle's radius and its circumference is one of the most elegant in mathematics. Let's look at this connection more closely. The radius of a circle, shown here in blue, is the fundamental measurement that determines its size. For any circle, no matter how large or small, if you know the radius, you can find the circumference. The formula c equals 2 pi r tells us that the circumference is exactly 2 pi times the radius. This means that for every circle, the ratio of circumference to diameter equals pi. This special number, approximately 3.14159, appears naturally in this relationship. This beautiful relationship between radius and circumference has countless practical applications. Engineers use it when designing wheels, gears, and circular components. Architects rely on it when planning circular structures like domes and arenas. Scientists apply it when calculating orbital paths of planets and moons.